thinking about it. So we're going to continue to review how muscle contracts once the recording has been engaged. It's definitely slow this morning. Okay, anytime would be fine. Anytime would be fine. So we'll just have to wait a moment. There we go. So we go back to the PowerPoint, and here we see a fine image of the structure at the synaptic terminal. The synapse is the gap between the synaptic terminal, the ending of the nerve, on top of the motor end plate. So acetylcholine binds to receptors. The action potential is allows sodium to come in, and sodium flows in both directions toward the negative charge inside the muscle fiber cell. And as that T-tubule has this electrical change in voltage, it releases calcium from the sarcoplasmic reticulum. That calcium binds to troponin, which causes the tropomyosin to rotate and expose the myosin binding sites on the actin, and the energized myosin heads pivot toward the middle of the sarcomere, and the muscle contracts. The muscle uses the actin fibers. Remember that are actin filaments that are attached to the at the Z line, and the muscle shortens. So then, as soon as the muscle contracts, acetylcholine acetylcholine is broken down. The channels close back. Calcium is reabsorbed into the sarcoplasmic reticulum. Active sites are covered, and then we have the contraction ends and the muscle relaxes. Okay, so skeletal muscle shortens as the thin filaments interact with the thick filaments, and sliding occurs. So read through this. Let's go through this again. So the nerve has a synaptic terminal. It's just above the gap, which is a synapse. And just below that is the motor end plate, where there are acetylcholine channels that open when acetylcholine binds. Once sodium rushes in, that allows sodium to flow in both directions, because remember, the inside of the muscle fiber is negative. All cells have a slightly negative membrane potential or voltage. So once that electrical change becomes more positive in the T-tubules, that releases calcium. That calcium binds to the troponin, and that causes the tropomyosin to rotate and expose the myosin heads on the actin. So these myosin heads fuse with the actin, so they're connected at the myosin head. The myosin heads have been energized by ATP, and they pivot, and they cause the muscle to contract by pulling the actin into the center of the sarcomere. Once contraction is done, acetylcholinesterase breaks up acetylcholine. The active sites are covered, and the myosin heads detach, and the myosin heads are energized again, ready for contraction. Okay, muscle tension is the pulling force of a muscle. Everybody knows that you're able to move muscles to pick up a glass, to use your body to help somebody move a table. All it has to come from the force generated by a muscle twitch. A muscle twitch is when a muscle actually increases its tension, so it contracts, develops maximum tension. So now we're measuring the force generated by a muscle. There's a contraction phase, there's a relaxation phase. It only takes about 15 and 16 milliseconds for the muscle to contract. Remember, a millisecond is a thousandth of a second. Then the muscle relaxes when acetylcholinesterase is going to remove acetylcholine, which had opened the sodium channels in the muscle end plate, the motor end plate, and once sodium rushes in, the contraction phase is started. Okay, so muscle fibers can some individual twitch. So when you're going through this PowerPoint, read here and let's look at what these processes look like. So you can see over time, if the frequency of stimulation from the nerve is getting shorter and shorter, or the time between nerve impulses, you can get incomplete tetanus where the muscle remains contracted, and you get complete tetanus when the frequency of the stimuli from the motor nerve, which causes contraction, those contractions sum, and you have the maximum tension that can be generated by a muscle. So summation of twitches, and notice the distance between these stimuli from the nerve are getting closer and closer. You can look at the distance between them. You can look at the distance between one stimulus and the next. You can see that the distance has been decreased a little bit. It's decreased even more, decreased even more. So as the stimulus of contraction from the motor nerves that are just above the end plate, motor end plate, and if you get the stimuli close enough to one another, you have complete tetanus, which means all of these individual twitches fuse to form a fine line of contraction phase, and then the muscle stays contracted, and then the muscle relaxes. Okay, so let's talk about motor units, which is the motor neuron and all the muscle cells it controls. The muscle can recruit the number of muscle fibers that the nerve causes to contract. And so depending on how much muscle tension you want the muscle to generate, you recruit motor units. So what do motor units look like? So you can see that motor neurons are located in the spinal cord. You have the axons of the motor neurons. Notice there are various nerves going to motor unit 1, which is this color, and it's connected to 3 muscle fibers. Motor unit 2 is the blue, 1, 2, 3, 1, 2, 3. So these are individual muscle fibers. So a motor unit is the motor nerve and the muscle fibers to which it is contracting. When these nerves all fire in this muscle, you will have tension in all of these muscle fibers. They would be shortening their sarcomeres and causing the muscle to contract. And if we have those muscles contracting and the more motor units are recruited, the stronger the contraction of the muscle. Okay, so all voluntary muscle movements involve sustained contractions in these distinct motor units, the force generators, by increasing the frequency of the action potentials and making more motor units contract. Okay, let's stop there. See if we can get it to stop. Stop.